Hello everyone, what I'd like to do in this video is prove to you one of the most famous theorems in mathematics, the Pythagorean theorem. What the Pythagorean theorem does is it relates the three sides of a right triangle. So let's recall what it says. And let's think geometrically also what it says. So if I have a triangle, a right triangle, if this is the hypotenuse, we'll call it C. The hypotenuse is the longest side of the triangle. The other two sides is what we sometimes call the legs. Let's go ahead and label this A, and let's label this B. Famously, what is true is that the square of the hypotenuse is equal to the sum of the square of the legs. A squared plus B squared. Or maybe, as some people say it, what's true is that the sum of the square of the legs, A squared plus B squared, is equal to C squared. Let's write this over here. Let's write it right here. Out of the way of that glare. Okay, what does this mean geometrically? So what is this saying? Well, geometrically, whenever I think about a quantity being squared, this represents the area of a square with side length A. This is the area of a square with side length B. This is the area of a square with side length C. So what the Pythagorean theorem here says is that if I think about a box with side lengths of C, so this is a C by C box, its area will be C squared. And then I think about a square of side lengths A. So this is A and this is A. The area here will be A squared. If I think about a square with side length B, so this is B, the area here is B squared. What the Pythagorean theorem here says is that this area plus this area is equal to this area. That's what it says. Okay, let's see why. I'm going to give you two different arguments. I'm going to give you an algebraic argument, and I'm going to give you a visual argument. Let's start with the algebraic argument. They both come from the same picture. So let's do it. How are we going to do this? Okay, let's give you an algebraic argument. Okay, so we're going to draw a square. Kind of a tilted square. So, and let's say this square has side lengths C. And now what I'm going to do is I'm going to create another box that kind of touches these corners. So let's make another box. And while this is definitely not perfect, what we have here is we are going to get four right triangles, and all four of them should be the same. So let's give these sides a name. Let's call this side here A. Let's call this B, which means that this would have to be A, and this would have to be B, which means this would have to be B, and this would have to be A, this would be B, and this would be A. So let's give you an area argument here. Let's think about the area of the bigger box in two different ways. One way we could think about the area of the bigger box. So one way to think about area, we'll write area way one, is to think that this larger box has a side length of A plus B. So its area will be A plus B times A plus B, or its area will be A plus B squared. Another way to think about the area is breaking this up into smaller pieces. Area way 2. Notice here I have a square and I have four right triangles. So the area of the square on the inside will be C squared. Plus, I have four of the same triangles. So I have 4. Now the area of a triangle is 1/2 base times height. Why? Well, if you think about a square with side length B and A, the area of this square is B times A, and I just want half of that. So the area of a triangle is 1/2 base times height. So 4, 1/2, base times height, b times a. Or we have that c squared plus 4 times 1/2 is 2. How about I write ab, since order of multiplication is commutative. So what I must have here is I must have that these two are the same. If you agree that I've calculated the area in 2 different ways, if you agree that these areas should be the same, then let's see what we get. So for space, let's write it in here. So what I must have that's true is I must have that a plus b squared must be the same thing as c squared plus 2ab. This must be true. So let's go ahead and FOIL this out. So this is the same thing as a plus b times a plus b would be equal to c squared plus 2ab. If we go ahead and FOIL this out, I'll get a times a. I'll get a squared. I'll get a times b, ab. I'll get a b times a. And then I'll get a b times b. I'll get a b squared is equal to c squared plus 2ab. So I have a squared, ab, ba, order of multiplication is commutative, so I have 2 ab's plus b squared is equal to c squared plus 2ab. Now try not to get too excited, but notice what happens. I could subtract 2ab from both sides, and what are we left with? The beautiful, the famous, the timeless, that a squared plus b squared must be equal to c squared. The Pythagorean theorem. So that's my first argument, an algebraic argument of why the Pythagorean theorem here is true. Let's give you another one. Let's draw a picture. Let's do another one. We're basically going to take this square I've drawn here and we're just going to rearrange the pieces. So here's another way to think about it. Okay, let's draw that box again. So, C, 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 C. So here we have that. Same box. Let's call this A, let's call this B. So that means that this will be A and this will be B. That means that this will be B and this will be A, this will be B and this will be A. So let's color code this a little bit. What I'm going to do is I'm going to make this inner box here, let's color this red. And let's color this triangle right here, let's color this one green. And let's color this one green. Let's color these two here blue. So what I'm going to do now is I'm going to rearrange some of these pieces. Okay, so the first thing I'm going to do here, I'm going to have the same exact box. Let's make sure I don't get in that glare. I'm going to have the same exact box. I'm going to fit the pieces in here in a different way. So what I'm going to do is I'm going to keep this green triangle right where it's at. So I will have the same green triangle right here. Keep that there. So this is A and this is B. And I'm going to take this triangle right here, this green one, and I'm going to rotate it so it fits right here so I get a nice rectangle. So let's rotate that so that other triangle will be right here. Okay. So right here, this length here will still be A. Hopefully that glare is not too much in the way. So let's think what I have here. If this is A, that means that this length from here to here must be A. And the length from here to here must be B. So what I'm going to do is I'm actually now going to take this blue triangle and I'm going to scoot it over. I'm going to scoot it over so it's right here. So I'll put it here. So this is A and this is B. All I've done is I've taken this triangle and I've scooted it over. Now what I'm going to do is I'm going to take this triangle here and I'm going to rotate it and I'm going to put it right here. I'm just rearranging the pieces. We're doing a puzzle. Okay? So let's think what we have here. Let's kind of make sure we finish these sides here. This is A. This would have to be B. This would have to also be B. So let's think here. I've taken account of this triangle and this triangle here. I've taken account of this triangle and this triangle here. So if these have the same area, they both have a side length of, they're both squares of side length B plus A. So they have the same area. So that means the rest of this area, this red area, must be here and here. And what is the area of this? This is B squared. What's the area of this? A squared. Since these red areas must be the same and this is C squared, we have the Pythagorean theorem that what must be true is that C squared must be equal to A squared plus B squared. It doesn't get much more beautiful than that. Here we go. I hope you enjoyed the video. We'll see you in the next one. Take care.